Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm very pleased to welcome Professor Arvind this morning. He's a professor at the MIT Computer Science Department, and he has done a lot of work that's very well known back in the 80s on data flow languages and architectures. More recently has been working on electronic design automation tools, and he also worked on a new chipset for routers. So he is going to tell us today about his work on memory models. I would also like to mention that Professor Arvind went to the same undergraduate college that I went to, which is the Indian Institute of Technology, Kanpur. Yeah. And I'm very, very proud of that association. So,
thank you. This is one of those talks which is really, you should ask lots of questions if you don't understand, because it's a little bit abstract, and some of you may know a lot more about it than I do, and some of you may not know anything about it. So this is one of a very, what should I call it? It's like a hobby of mine, to indulge in memory models, and I've been doing this for last almost a decade in this. Most of the papers I find extremely defective in this, and then I got into Java memory model. So I went to Guy Steele, and he says, well, yeah, it doesn't make any sense. This is before they had decided that they were going to abandon it. Then the new Java memory model came out, and that's, in my opinion, still has lots of problems. First problem being nobody understands it. So you can make claims about it, and it will be very hard to defend it because everybody says, well, I concede to so and so. There are problems in that model. So, and the problem is exactly the same if you're talking of multiprocessors. Exactly what is the meaning of load and store instructions. In some sense, what I'm after is there should be a very precise way of saying these are the legal behaviors, in a shared memory program, and these are not legal behaviors. I want that boundary drawn absolutely precisely, so that there is no ambiguity about it. This is not about implementation, this is really about specifications. When you buy a PowerPC multiprocessors or a IA32 multiprocessors, what are the legal behaviors if you're programming an assembly language? Okay, so this work is done with Jan, who's at Sun in Burlington in Boston. I think I wrote down some of the things which is the organization of this talk, but again, we can discuss any of these things. I'll very quickly review sequential consistency and serializability from the point of view of this talk, how I want to look at it and how we'll go ahead with this. Then I want to talk about local reordering axioms and tell you why I want to talk about that. And then we'll get into store atomicity, exactly what I mean by store atomicity, and it's one of those things which is easier to explain by looking at counter examples. What happens if you don't have it, as opposed to what happens when you do have it, right? So we'll look at a few examples like that. At least one of them is very, very surprising to me, and we went for almost 2 years without recognizing it, but without that, of course, the proof doesn't work and the results are just wrong. And then this thing, execution graphs and enumeration, etc., is just, it follows trivially from all that. So, if you buy the earlier parts. And then, I can talk a lot about implications and applications of this. What does it mean for speculation? What does it mean for multi-threading? What does it mean for well-synchronized programs and stuff like that? All right, so everybody knows sequential consistency. There are two views of it. It really goes back to Lamport's paper in '79. So one is the operational view, which I like very much because it's unambiguous. You toss a coin, you say, you go and execute an instruction, this processor. And whichever guy wins, he goes and updates the memory or reads it. and then you toss the coin again, and then the next guy does it. So there is no ambiguity. If you can't generate a behavior in that manner, then it's not a legal behavior, right, of the system. So this is the good part. The bad part is it doesn't give you enough insight into, which store instructions I'm allowed to read and so on, So it doesn't help you tie with a load with a particular store operation. The declarative view is also due to Lamport, which is ultimately we should be able to understand the behavior as some interleaving of the requests that are coming from various threads, from various processors in this, right? I mean, that's the model people want in Java as well. But I think the reason why this is kind of important is I want to maintain this idea of memory as a monolith, right? That it's some big thing, even though there are lots of loads and stores going into it. I want to be able to think about it one at a time, ultimately, right? That this load instruction, this store instruction was issued after that. Another load came from here, therefore it must read the latest value that was stored, and so on. So ultimately, I don't want to worry about parallelism in this, right? I want to see, view this as, and that's where linearization or serialization comes in this. So let's look at this. What do people mean by, and I'm going to use the word linearization and serialization sort of interchangeably, but people who have worked on this problem, they will get upset because they have a very specific meaning for linearization, but the level at which I'm talking, I hope that issue won't arise, right? So let's build our intuition about serializability. Okay, so we want, in some sense, a total order on instructions that are in the, various processors that are executing, and some interleaving of them. So one way I like to think about this is, suppose there is a load, so L will stand for load and S will stand for a store instruction all through this talks, and these are addresses in this. And usually when I write X and Y, it means different addresses from each other. So this load in some thread sees this store value, and this load sees this value, right? So this is a very simple two threads, this is the values you observe in this, and by writing equal to 2, what I mean is this is the observation, right? So when this load Y was executed, it actually went and read this one, and therefore the answer is 2 over here. Is this clear to everyone? So what are there are many possible serialization of this, right? So for example, I can order these instructions in this manner, right? Actually, the only constraint here is that the store must come before the load, right? If I'm going to be reading, it must come before it, right? Otherwise, it's fine. And you could have done it like this, and you can do all kinds of permutations and combinations of this. So all these are legal linearizations or serializations of this. Now, I want to focus on the second condition. If you do 2 stores to something and they are ordered in some sense, and then you do a read, then you do a load, you are only allowed to see the latest one in this. So suppose I change that example, so that instead of Y's, I have X's here, right? So somewhere I'm reading this one, and somewhere I'm reading, to the same location I'm reading this. Now you already see what will happen if you look at the linearization. I just enumerated all of them over here, and you say, but wait a minute, you can see this one. And why not? Because you have overwritten X, so you're only allowed to see 2 in this, right? So in case of overwrites, you're only allowed to see the latest one in this. So this is not allowed, this is not allowed, this is not allowed, etc. Okay? In other words, these are the only 2 possible linearizations of this particular thing, just by changing that X to Y to X in this case. So when you're talking of the same address, this override thing becomes quite important. It's a constraint that you have to worry about. So most of you probably already know all this. I just wanted all of us to be on the same page. Is this clear to everyone? Okay. Okay. Now, everybody talks in terms of sequential consistency, right? And sequential consistency will have this property called store atomicity, but it has, you simplify your life by saying all the instructions are going to be executed in order, right? I mean, that's the essential model behind it. The fact of the matter is nobody follows that rule. I mean, certainly we don't do it in hardware. I mean, instructions get executed out of order. Compilers take full advantage of it. They don't adhere to the order in which you present instructions. You know, they will do analysis, data flow analysis, you know, compute things, etc. So people say, oh, this is too difficult. I can't remember. But yes, it's difficult because the explanation in the literature of what are the legal behaviors, if I allow you to do this, are very, very problematic. You know, I mean, even experts don't agree on what behavior is allowed and what behavior is not allowed, right? But we should not confuse that fact that it couldn't be simpler. I mean, you know, if you had a better explanation. So here is a table of the kind of instruction reordering you may want to allow, right? You don't have to allow all of it. I'm just looking at this as a fairly common thing. Let's see if we can all read it. So suppose the first instruction is some sort of a plus instruction, and the next instruction is also some sort of a plus, register to register op, right? So obviously they can commute unless there is a data dependency. Yes?
Are you ignoring floating point? Where the plus do not commute?
Yes, so I'm ignoring those kinds of issues. If you don't want, you can easily elaborate this table, say if it's a floating point operation, no commuting is allowed, right? So absolutely fine with me. I'm just saying one of the strengths of this work is this is a parameter in the thing, right? So store atomicity is one property I will insist on, and as far as the reordering matrix is concerned, you pick your own, right? I just picked one like this, and all the results are totally independent of this, right? Okay, so let's see what else makes sense. So I'm saying a branch followed by an add, you can always commute it. So why am I saying this? Because I'm going to assume infinite register renaming. You know, you can have as many names as you want. So if you want to do R1 plus R2 beforehand, just give it a unique name and then use that name from there on. What is interesting is load store operation. So if you have a load X followed by a store Y, under what conditions you can commute it? So you have a load X followed by a store Y, you can commute it only if the address is different. Otherwise it must be done in order. Certainly the same thing is true for store things, right? Loads are different. I mean, you know, two loads, load X, load Y, you can commute it anytime you want. But there could be weird data dependencies, you know, because first load may be producing something which is being used as an address in the second load. So barring normal data dependencies, there is no reason to constrain loads. And this is what we take advantage of, both in compilers and in hardware. You know, at runtime we exploit this. And we will allow memory fences in the system. All architectures these days have memory fences. And basically a memory fence essentially says that any time you put a fence, then a load operation, for example, can jump over it. So if I have a fence and there was a load or a store before it, it can't commute with the fence. It's a memory fence. I mean, the instructions before that will remain before that. Instructions after that will remain after that. Make sense? You know, this sort of commuting thing. So this is, I'm just showing how loads can be dependent on each other. So now let me just define what I mean by serializability slightly more formally. So it has to have three properties. You know, I want to be able to put everything in this total order, right? And this thing here, in the case of sequential consistency, was often referred to as the program order, or the order in which instructions were executed on a given thread. So if two instructions are going to be ordered there, then they must remain ordered in the total order. Whatever local ordering you have, and this idea absolutely generalizes. So if this is a partial order locally, as I showed you through this matrix, then only partial order has to be preserved in the total order. Right? So there is no conceptual problem in doing that. And what is this saying? That if this load was going to be reading value of some store, it must come before it. Actually it cannot come afterwards. Must come, the reader must come after the value has been stored. And the third one is this double store property I was talking about, that if the address of load store is the same, and you claim that this load is reading this store, then there cannot be another intervening store. Because if there was another intervening store, then this will get obscured, and you will only be allowed to read this. So it says there does not exist such a store. Yep.
Who defines the source? Who defines which store?
So we will have a choice, and as the execution progresses, right? So at any given time you will have candidate stores for a load. Right? This load is allowed to look at these 15 different stores from various threads, right? And you pick one, and the one you pick is the source at that point.
Another way to say that is that you have to provide the witness less than and the witness source function as well.
Absolutely. Right. And that's exactly the thing we will make very, very precise here. In sequential consistency, the kind of description I gave you, that doesn't come through enough, but I'm going to rely on this function, all the time, and you will see examples of this. Oh yeah, this is just showing you pictorially. So you can't observe this, right? I mean, that's the whole point, because there is an intervening store in between. Okay, so I think now is the real meat, to understand where things go wrong. So let's look at this example. And what is it saying? You have store x1 followed by store y2 load y in thread 1. And in thread 2 you have store y, store x followed by load x. In other words, they're doing stores in the opposite orders. Right? One is sx xy, the other one is xy sx. Alright, suppose this guy, yes, I can draw a graph, which is showing these dependencies. I haven't read anything yet, right? These are just the control dependencies enforced, implied by these threads over here. Okay, now suppose this guy reads 3. In other words, he's reading that fellow over there. Okay, so he had a choice, right? He could have read either he could have read this one, or it could have read this store. It chose to read this one, so therefore I have drawn an arc. So far so good. Now the question is, what can this load do? Right? I mean, is this allowed to see this one or not? Any opinions on that?
No.
Not allowed to see one. Why? Because this guy witnessed this thing, so therefore we must have gotten this far. Right? And if we got this far, then, the double store property will. So this is, if you're allowed to see this one, it will be a violation of serializability. In other words, there is a path of this sort which is implied because you observed, and if you go along that path, then you can see that store x4 is obscuring store x1.
It's also the case without fence instruction, right?
No, fences are there, in this, because these are different addresses, and I don't insist that they remain in order then. So fences are important. Was that the question?
Yeah. So I thought
In my picture,
always read 4 even without the fences in this program.
no, because if there are no fences, then these two will be at the same level, right? And there is no reason for this and this to be ordered, right? According to my reordering axiom, right? So fence was important in this case. So now what I want to do is I want to disallow this, right? Because I know that if people are allowed to read this, sooner or later I'm going to get confused by this. So one way to disallow this is, whenever you observe this, whenever this guy observes this, I draw an arrow from here to here. So what does this arrow say? You're observing this Y, you're observing this store, right? So you're saying all the other stores to Y that came before you must have come before this one. Otherwise they will remain candidates so that you can see them, right? And you want to say, no, it's obscured now. You can no longer see this the moment you see this. And I can enforce this in my graph by drawing an edge of this sort. And that's the rule, that predecessor stores of a load are ordered before its source. Yep.
Terminology may be a bit confusing because the reader absorbs only the number 3.
Right.
Absorb the load.
No, say it again.
I know what you mean, that he comes immediately. SY2 comes immediately after SY3. But when you call it absorb, not you really can absorb only the number, not the load itself.
That's true.
Just a matter of terminology, maybe. Maybe absorb is a little bit confusing term.
Okay, so I'm using it in the following sense. For any given load, there are stores that it can observe, right? So before this observation was made, there were 2 of them. The moment I have observed it, this one has become obscured, right?
How would your graph change if you stored 3 both times?
I don't pay attention to the values being stored.
Okay, so just...
Right, because then it will get into equality checking and it will become really messy at that point. And in any case, machines won't do that either. I mean, they're only looking at addresses in this case, right? So far, so good? Now let's look at this example. So what's happening here? Store X, load Y. And the other one is store Y, load X. These 2 stores are automatically ordered because they are to the same address. So according to my ground rules, you can't, compute it. So again, if you were to draw, these are totally ordered threads in this manner. And as usual, let's observe this. And so you can guess where I'm going with this now. So what is this X, load X, allowed to observe? No, again, why? Because this observation, which was about some other address, still implies something about where you got, and therefore, you should not be able to see the old value of X. So you can again see this, yes?
Are we allowed to commute instructions above the fence?
Normally yes, but because it is store X, they don't commute. Right? I mean, I could make it clearer by writing a fence there also. So everybody agrees with that. So how can I prevent this one? Any ideas? What is the general observation in this case?
You draw an edge from the store to the load that observed it.
store
Some kind of finality comes in.
This is actually very interesting, because we missed it for several months. So you'll draw this edge. And what is this edge saying actually? See, you observe this one, right? And actually you are making an assertion you came before this fellow. Because if you came after it, you could not have observed this one. Right? So this is very important to understand, that not only predecessor stores got ordered with respect to your observation, successor stores are also getting ordered with respect to you. You have to find your exact position, in this load store chain, in some sense. So that's the ground rules for this. The successor stores of a store are ordered after its observer. This is how things were for quite a while, until I should say about 4 months ago. Right? So the thing is, what I showed you is this situation. Let's suppose you observe that, then there must be an edge like this, and there must be an edge and what is really surprising is this is not enough. Okay, once this, we discovered this wasn't enough, it was truly a shock to me, that how can it be? So let me show you. Suppose you have a situation like this. So you have some computation here, which comes before, which is before both of these.
So
And you have some computation here which is after those stores, right?
I was suspicion that when you say it is not enough, what you mean is that you draw the graph like that.
Right.
The acyclicity of that graph is not enough to ensure sequential consistency.
Exactly. You will not be able, or technically you will not be able to serialize it.
Yes, that's true.
Right? You will not be able to build this total order, and we intuitively understand that the total order is very important because that's the thing that gives me this monolithic view of the memory. Right? The things happen one at a time, which I want to keep, right, in this case.
Here the two ovals are the same computation.
No, they could be, just general computation, right? I'm just building some intuition about what is very surprising here is, suppose this guy observes this, and this guy observes this. According to the rules I have shown you, no new arcs have to be drawn. Let's assume there is nothing else going on. There is no loads or stores to X here and no loads and stores to X's here. Right? So no more edges have to be drawn according to the two rules I gave you. And this is what I thought, right? These are two independent observations. How can they possibly affect each other? And this is fascinating, that it turns out that the argument goes something like this, that these pairs in serialization must come either like this or like that, but they cannot come like this because that will immediately violate the double store property in this. So if you insist that this pair must, though you don't know which way it will go yet, I'm just saying, suppose in your serialization you want this to go before that. This pair comes before this one. This is what I mean by this thick arc over here. Or it could be this one comes before that. Right? You can see in both cases, regardless of how it is, operations here will happen before operations here. mean, this argument is very simple because this is absolutely symmetric. So if this implies that this comes before that, then the other one will also imply this comes before that. So you say, what's going on here, in this case? In other words, any time you have mutually independent pairs of operations, their mutual predecessors and successors get ordered with respect to each other. And I could construct, real examples for you and show you, which I have to draw these edges. So this is the. Now there is something very subtle going on in this. So there is a temptation at this stage to say, well, if they're going to come in some order, let me pick one order and move with that. You can't do that because another goal I have is all legal behaviors, should be permitted. So if you pick one of the two orders, then you'll have to prove that it doesn't matter. You haven't ruled out any behavior, which is absolutely not the case. These two, which order you pick has consequences, for what behaviors are allowed and what behaviors are not allowed. But they, in a subtle way, impose a constraint, so that stuff must come before this. So here is a detailed example showing, how this thing will happen. Let me just show you. Roughly the graph looks like this. So there is this store X which comes before these two, load Y's, and you have I'm going to be reading this load X, and there is another store to X. This stuff I'm doing here, and these are the two store Y's for this and this. This stuff I'm creating just because I want to create a dependency over here. So let's make it observe this thing. So this guy observes 2. I draw this. I hope you can relate it to the previous diagram. And this guy observes 4. Right? So now we are in the situation what I showed you earlier. How can the dependency be created? Suppose this guy observes this. So what has happened now? These two stores come before all this computation here, right? And this comes before these two. And this is exactly now where the problem is. The question is, are you allowed to see one? Or has that X become obscured in this case? If you do that, because what will happen is you should be able to argue that there is a dependency of this sort, and the second store X will obscure the first one. I think you can read the details of this example later on, but the main point is that you have to draw such an edge. So again, the reason I said this is very surprising to me is ideally, when you're doing some observations in this part of the machine, some observations in this part of the machine, and so far, as far as this address is concerned, there has been no commonality, right? You would have thought that, they can go on merrily from there on, but in fact, they, in a subtle way, impose constraints on other things that are going on in the machine. So as you can see, what I've been doing here informally for you is I've been sort of explaining the computation in terms of graphs. Because in my model, I don't want to have memory, I don't want to have caches, etc., because then the argument gets very, very complicated, and people are always talking in terms of if the store has been performed, if the store has been completed. None of those concepts make sense to me. I want to think of stores only in terms of witnesses, what a load sees, so that I don't have to answer this question of what does it mean to do a store operation, which is really very, very difficult question in real machines. What does it mean a store has been done? Because you can keep balls in air forever in this case. So nodes are labeled with the operations, edges show data or control dependency. Now this is important to understand. What a processor does is always intra-thread dependencies. I mean, when we talk of out-of-order execution, etc., that's only about one processor. So that reordering matrix I showed you has only relevance for a single thread. And any time only way you can cross, boundaries is by doing a load or a store operation, by load operation. Because when you do a load, then you start drawing edges across threads. That's when you're observing something that somebody else is doing. And again, there is this notion that a load has a set of candidates, stores that it can observe. So that's the potential non-deterministic step, and enumeration of all behaviors will involve viewing them one by one. Just keep enumerating, tossing a coin and seeing what you get. So here is the definition of candidate stores. Right? So if you have a load, what all it's allowed to see? Well, the address of the stores must be the same. You're only allowed to observe that. And I only let you observe the oldest one in the chain. So if you have several loads, you must first go and observe this, then observe this, then observe.
You mean stores?
No, loads.
Loads observe stores.
Right. I mean, you must resolve this, what I mean, right? I don't want you to do them out of order, otherwise it'll get too messy, and you will have to go and erase things which I don't want, right? So, and S has not been overwritten, so that condition hopefully is very clear to everyone. In other words, given an execution graph, you'll be able to immediately algorithmically compute which are the stores that are candidate stores in this. And in some sense, this is a chicken and egg kind of a definition. I have already motivated this, but this is the definition of store atomicity. So now I say, what does it mean for store operation to be atomic? I mean precisely these three conditions. Predecessor stores of a load are ordered before its source, and successor stores of a store are ordered after its observer. And for independent things, mutual ancestors of unordered loads and are ordered before the mutual successors of the stores they observe. As long as your graph has these three properties, I will say it has store atomicity property, and also it will be serializable. You can mathematically prove, then you can build this order on this stuff. Now, why am I insisting on this property? You see, the thing that has always amused me is I'm into cache coherence protocols, so I look at lots of different cache coherence protocols, and cache coherence protocols actually don't depend on the memory model. Regardless of what memory model you have, what's going on inside the processor, your reordering instructions, and people are debating whether the answer is right or not. The cache coherence protocol says, oh, go and zap everything, and then update it in this manner. And this matches my intuition, because what's happening is cache coherence imposes store atomicity. Cache coherence has nothing to do with the local reordering of instructions. And so far we have mixed up these two properties. So I'm saying, okay, let's make it separate. So we can talk now of memory models which have store atomicity property and which insist on sequential execution of instructions. That would be sequential consistency. Or you can have, store atomicity, and you can have some reordering of instructions according to some, axioms. And that will be a more relaxed memory model. So these are two orthogonal properties of memory models.
I'm not sure I understand your third point here, which is what do you mean by mutual ancestors and mutual successors?
So I had two loads here, right? And there was some computation that happened before them because there is some dependency on these loads, right? So whatever is happening here, and then if these guys observe some stores, right, which have successors, all I'm saying is that these successors actually must come after those predecessors over there. That even though these loads and stores may not be ordered with respect to each other, they already impose restrictions on things that were happening.
I have a question.
Yeah.
With this definition, again, with respect to a certain witness less than and a certain witness function on how you match loads to the source store.
I'm assuming you can pick anything in the candidate stores, right? So that part is totally not deterministic. What deterministic part is, the set of candidate stores is absolutely fixed, right? Given a graph that's unambiguous, which are the stores you can see. But which one you pick, I'm saying pick any amongst the candidate stores. Is that the... Maybe I didn't understand the...
So you are presenting a way to add more edges. So there was, are you going to show how you resolve that using the story?
I thought I did, but maybe I went over it too fast.
No, so here you just showed how the old story doesn't help with this example.
No, and this is the edge you will have to draw, the dotted edge. Basically what will happen is, so you have to imagine dynamic execution of this, right? So suppose these observations have been made, right? And you do this store. The point is, before you do any load, you have to make sure that the graph is consistent at that point. And that's the time when this edge will be drawn.
So why did you draw this edge? I don't understand.
Okay, because let's look at these two loads, right? And they're observing these two stores.
Yeah.
They're independent of each other. This is a mutual predecessor of these two.
Okay.
And this is a mutual successor of the things that were observed.
I see, okay. Because
Right.
it has a sequence of edges from each one.
Exactly.
So I see, and therefore you add the edge.
Exactly. So from mutual predecessors,
So, but the thing is that how does that create a cycle when you say load X? So you I want you to show.
so the moment I draw this edge, now I have obscured this, right? You can only observe this one now because of the double store property.
I see. Oh, so now what will happen is
You can only observe this.
if there was if load X returned 1, then that means that you have to add an edge to store X8 and that will create a cycle. Something like
Yeah, or in my way of thinking,
Or you can just-
now it's no longer part of the candidate stores.
that. Okay. All right.
Only this is part of the candidate for X at this stage here. By drawing this edge,
And now you
Yes.
got a proof.
that's right. So given these three conditions, you can show that the linearizability will hold in this. This will restore, somebody's faith in formal methods, because Jan and I are so deeply seeped into this, right? And the fact that we could have missed this, so, and that's the reason why proof didn't work before. Yes.
Where the rule comes from again?
What is this rule?
Yeah, where it comes from.
So basically, just imagine everything given on this except for this edge, right? What that will suggest is, if you look at this load and you ask which are the candidate stores for this, right? You say, I can certainly see this one, and since I follow chains from here and there are no chains, so I can observe this one too. So I say, I can observe both of them. And then you say, oops, if I observe this one, I'll get into trouble. Because if I observe this one, you'll create a cycle in this graph.
Well, once you assume that there's this a road that is just grown, right? There will be a cycle, but I don't understand where you make the rule.
If you observe this, you will not be able to put these loads and stores in a sequential order as we need to for serializability.
Okay, that's the part that is
Right. We can work out the combinatorics of this. You will see it. So if you want to obscure it, if you want to make it impossible, one way of doing that is to draw that edge. I mean, the interesting thing in this is, please notice, even after drawing that edge, those two stores, I mean, these pairs are still not ordered with respect to each other. This pair and this pair are still not ordered with respect to each other. I mean, that's a very important point. If you ordered them, then you would rule out some legal behaviors further down the line. So if they are not ordered, you want to keep that property, that they should remain unordered. Things should be ordered. I mean, that's where real semantics are coming in. They should be ordered only if they must. In other words, they must be ordered if they are going to be ordered in every possible serialization. So I should actually give you some example. Yeah, go ahead.
So you said you had to prove that after adding these three orderings, then
Right.
you added these three.
That's right.
You also prove that it's the most general order that can
That's a good question. So the question you are asking is, can I prove? I can certainly prove that if you leave out one of these, you'll be in trouble. Right? In other words, it won't. Yeah, so proof works both ways, right? In other words, if you have these conditions, you can show it can be serialized, and it's trivial to show that if you left out one of them. I mean, I've already shown you the examples, right? That constitutes a proof that if you left out any of these conditions, it won't serialize, right? So it's a necessary and sufficient condition.
I think what Madan is asking for is a different thing. He's saying, let's say that you have an execution that is serializable. That you can just, the definition of that is there exists a less than relation and a function that maps, every load to a source store. Then you should be able to construct the story, right?
So that's, okay, so now you're taking me in the direction where things get very, very subtle, that if all these things are online, they have to be true all the time. So you're not asking a declarative question at the end.
Yes.
Is there a possible, otherwise things will become undecidable again, which people know about SC also, right?
Right.
Let me show you some implications of this. So you can imagine now how the graph generation will. Yeah, sorry.
Maybe not understand. So the question was whether you miss any possible order or not, right? That was the question. I think the answer is you don't miss.
That's right.
Because all the conditions are necessary, and therefore you cannot possibly outrule any legal behavior.
No. I can draw extra edges, right?
Say it again.
I can draw extra edges,
Yeah.
which will, any time you see two stores, and if they were unordered, just draw an edge between them.
No, but
The graph will still have store atomicity.
if only you insist on your condition, nothing
Right.
else,
Right.
then you don't rule out any.
That's right. That's right. So that's a very important detail, though. You'll have to.
This was the question. So just imposing the three axioms rules out nothing.
Rules out nothing, right?
Well, I suspect that's true, but I don't think the arguments presented here have actually demonstrated that. These might be sufficient conditions, but not necessary ones. Might be some, two of these and some weaker third axiom might suffice. And we haven't actually argued that point.
You're asking a very good question, and I'm getting a little bit.
Perhaps we should, I think we should.
All right. Okay. So this is, I'm just giving you some idea of how you will do this. So I'm saying, keep generating the graph without executing any instruction, right? Because many control dependencies are obvious, and at some stage you will get stuck in that, and then you start executing instructions data flow like, but don't execute any load instructions, right? So again you will get stuck at some stage because there is nothing to do, and then at that stage you will make sure that the graph is consistent, and you will go and say, give me the candidate store for this load. And there are two levels of non-determinism in this, because you can resolve any load, right? Load X, load Y, load Z, etc. And any given load has a candidate set, and you can pick one of them. So enumeration of all behaviors will imply, some sort of, walking over that space, non-deterministic space. So this is the point we keep coming back to, that if you draw any unnecessary edges, you may keep the serializability but rule out some legal behaviors. And this is what all machines do. I mean, the very first thing machines do is, the moment you do two stores, they immediately obscure one of them. When cache coherence protocol doesn't wait for a load operation to be done, when you do a store, that's the time when you say, okay, everybody zap it from their caches and go and write it. In that. So there is at most one owner at any given time, but you have ruled out behaviors when you do it like this. I don't have time to do all of them, but let me discuss some of them, right, over here, some implications of this. So Sun's, Spark's total store order violates store atomicity. Why? Because as architects we are very keen to give some, we have store buffers, you have a whole chain of loads and stores sitting in the queue headed for the memory, right? And somebody does a load. You say, well, let's just go and take a peek in the queue. If there is a store to that thing, then I go and read it. Nothing wrong with that, but if you do it and not at the same time advertise that store to everybody else, you'll get into trouble. Because now you have given preference to this local thread. And I think this is a terrible idea.
You're saying that TSO violates store atomicity and still ensures serializability.
That's actually, I didn't ask that question. Probably not, but no, it cannot. It'll violate it.
It will violate it.
Yeah, it'll violate it.
I thought that everybody would want to assure.
Oh, I know, but you see, these things, you have to understand the history of this is nobody sat down and said, I want store atomicity. Architects do exactly what they please, right? Then everybody keeps trying to explain, what the hell happened here, right? Because it's such an important hack, to be able to read the local store queue that, you say there is a problem with this. They say, really? There is a problem with this? Okay, let's fix it in the next model. Because most of these problems won't show up easily, But I'm saying that this should absolutely be prohibited going forward, because we're going to have multiple threads on the same processor. And we're going to have multiple, cores on the same chip. And where do you draw the boundary? Who are you going to give privileges to in this? So, in my opinion, it should be all or nothing in this. So I'm not in favor of models that don't preserve store atomicity. But now let me show you at some level a bigger shock. And one version of this paper was, we said, we finally discovered something that we can actually convince the whole world with. That if you are doing address speculation, which all machines do these days, so you have load X followed by store Y, right? You just assume X and Y are different and you go ahead and do it. And if they turn out to be the same, then you say speculation failed and you roll back, right? This seems obviously correct, right? Well, I can show you examples. This is the example where you can generate behaviors this way that you will not be able to generate if you did not speculate. So you say, oh, what do you mean speculation? Then it's just wrong. So you get into this language issue, how should we talk about this stuff, right? But I discovered after submitting the paper that people had already made this observation. So this example, not exactly this example, but similar thing appears in a paper in 2001. And their point was that if you are trying to enforce sequential consistency in a speculative machine, you have to do more checking than just saying that these addresses are different. Otherwise you will admit behaviors that are not permitted by SC. So anyway, so we were very thrilled that we had discovered something. It turned out it was already known in this. But what this example shows you is, so why does speculation allow more behaviors? And I should have drawn more slides for this. See, it should not be a surprise that if I get rid of any edge in my graph, potentially, I will introduce new behaviors, right? Because I have made it less constrained. I have deleted some edge. This is precisely what address speculation does. Normally, load X, store Y, you will have an edge going, you can't go ahead until you have decided X is not equal to Y. Right? But in speculation, you say, no, there is no such edge, keep going. If it turns out to be wrong, we'll just throw away the whole graph. We don't care. I mean, that's what the speculative model is, where you actually discard things that you have already done. In this case. All right, so now I say, I know that people are not going to stop doing address speculation. It is so important in modern machines, you have no choice. So should these behaviors, extra behaviors, should they be called legal or illegal? Any opinions on that? Or do you want to see the example how these new behaviors come?
Well, what happens when you roll back? Or when you mentioned rollback before, is there some sort of validation step and then?
Yeah, I mean, so you can put a predicate in the graph saying that if this doesn't turn out to be true, just throw away the whole graph, right?
Well, is it really that you've got the wrong assumption here? That if you're just assuming that just the address is being different than what you need, and otherwise you runtime check later on.
So what is that check? Describe. But that's exactly the.
You're too eager in saying this is permissible.
Right. But what I'm saying is I'm really asking you the meta level question. Why should it not be permissible? I mean, what are the grounds for rejecting it? Right? Yes.
If I get it right, the load instruction does two things. It loads something to a register, and it acts as a witness that something happened before something else. And when you undo the first one, you may not undo the second. Is that the problem?
That's right. That's exactly the problem. In this, I mean, another way to understand this is, let me just draw these arcs here. So what's happening is that this guy observes this one, right? So you got this far. And this guy observes this, right? So you got this far. So at this stage, this should not be allowed. Right? Now you can see what will happen in speculative execution on this side. Right? I'm loading some address here, and then I'm going to be storing in that address. And if you were really honest and didn't speculate, then you'll have to wait until this is done. But when you do speculative execution, you say, it's okay, go ahead. In other words, you're saying this Y is going to be different from all this. I don't care. And that assumption turns out to be true. But effectively what you did is, by relaxing this thing, it's like as if you executed this before, and you will be allowed to see value 2 over there in this. Yeah. No, the speculation turned out to be correct in this. The speculation is, this was the speculation. You did not know whether it should be Z or not. It is Z, right? And still, it behaves as if this happened before this. It really is very, I mean, I was thrilled, when we discovered this. But now I have a meta-level question. Okay, so we agree it's new behavior. What should be the grounds for rejecting it?
It's not serialized.
Sorry?
You reject it because it's not serializable.
It is serializable. See, that's the interesting part in this.
Serializable, but doesn't satisfy store atomicity? Is that what the
No, it satisfies store atomicity. I mean, I'm saying it should not be disallowed. You see, previously people just said it introduces new behavior. I'm saying great, it introduces, just as TSO introduced new behaviors. In case of TSO, I'm saying the new behavior should be disallowed.
Right, so in this case, the new behavior will violate sequential consistency, but won't violate...
Exactly, it doesn't violate store atomicity. It just, you relax the reordering even more, by going to this speculative way of executing things, right? And in fact, if you insisted that this behavior be disallowed, and your machine was doing address speculation, you'll be climbing walls. I mean, it'll be so tough to implement
But
this.
for example, if there was a fence between those two instructions, between the speculation and the next one,
Then you can control it.
then you would, what would you do then in that case?
But you know what architects doing these days? They are also speculating about fences. So they start saying, yeah, I know there is a
Then
fence.
you can get into trouble, and then you
Yes.
won't even be able to...
That's right. So I'm saying that I'm now giving you independent judgment. I'm saying, well, let's say at least executions have store atomicity, right? And furthermore, I'm saying whatever reordering goes on according to that matrix I showed you earlier,
Yeah, sure.
right? So that's pretty, concrete things you're being given for legal arguments in this. Yeah, I'm sorry I'm flying through all this. So basically speculation is a delayed enforcement of dependencies and as such do not necessarily violate store atomicity in this case. It's problematic if new behaviors due to address speculations are not included in the memory, but the implementation does. I'm really arguing that address speculation actually simplifies the theory underlying it. Because you're doing less checking in some sense. You want to give architects maximum freedom going forward. You're saying, I don't know what your machine does today, but if you want, you're allowed to do this also in this. Just one more thing, that whatever I'm talking about is really a very low level model. I mean, you do not want to bother programmers with this level of thinking. Can I take 2-3 more minutes? Yeah, okay. So programmers absolutely cannot think at this level. I mean, they want to deal with much higher level things. So you want to have some discipline in programming, guards, transactional memories, whatever you want, some high level idea. And one idea that was very popular, for a long time was this idea of properly synchronized programs, except that I always had difficulty with the definition of what was a properly synchronized program. And the essential idea is as follows. Divide the variables in two classes. Ones that are going to participate in synchronization or locks of some sort. By definition, there is going to be a race for them. And you define the rest of the variables as the rest of the variables. Right? And there should not be any race for the other variables. Which will mean, in this case, very precisely, that for all non-synchronization variables, the candidates set is always 1. There is only one value for that x that you can read. By definition, in this, if the program is properly synchronized. And you can, and they can also, there are implementation advantages too in this. So it's kind of important to look at this example very quickly. So you have store x being guarded by some lock m, right? And what that means is that there is going to be an edge either like this or like that, because lock regions must come in some order. And the moment you do that, you can see that x is always going to have a unique value. There's going to be a single store, in that. And this load x is being guarded by lock n. So So this will not be a properly synchronized program, because this guy can run in a race with them. So that's the idea, because its candidates set, it can read both. It doesn't care about that. Now, the only thing I want to say about transactional memories at this stage is, remember, load and stores themselves are the degenerate case of transactions. It's like a transaction that consists of only one instruction, either load or store. So whatever I'm saying, has to be consistent with the semantics of transactional memories, though we will have to work more on the semantics of transactional memories because there's more going on there. But at least I have identified the bottom in this. You can't violate whatever is being said in today's talk, because clearly a single load and a store forms a transaction. Right? So that's the whole, and in transactional memories this will be allowed. Right? This is the same example as what I showed you before, because you can do it optimistically, this load X can get in. So there are definite advantages in programming, when you think in terms of and this is the last slide I want to say a word about. Okay. Now what Bill Pugh and Sarita did was they actually were asking a slightly different question than what we were asking, because after much powwow, we finally understood what each side was saying, because it was like talking through a glass wall for a long time. I kept saying, your semantics makes no sense to me. They say, your question doesn't make sense to us. They kept telling me. So the issue is the following. I said, look, at the very least, you have to give me a semantics of Java so that I can enumerate all the legal behaviors of a Java program. Right? I mean, if I can't operationally enumerate all the behaviors of a Java program, then I don't know what kind of semantics you're talking about. I mean, how are we going to decide whether something is legal or illegal? So this is the question I have. The question they had was, sequential compilers already do gazillion optimizations, and they did it kind of in a democratic way. They went around and say, well, which optimizations must be preserved? Right? Literally, I mean, this is how this debate went on.
I thought that at the end they did answer the question that you asked for, which is...
They didn't. You see, so theoretically they didn't answer the question in the following sense. The conditions that are there in the current Java memory model, to understand whether the behavior is legal or not, you may have to look infinitely in future. So in some mathematical sense, it's a little bit bogus. It will turn out to be undecidable. You cannot figure out, and it's primarily because of, optimizations.
Are you saying that they can't give a fully online definition
That's right.
of what's going on? And one thing you want is an online definition.
Yeah, I mean, because I don't want to ask the question after the fact. I want to know at every given stage what is feasible, because all interesting programs, including the programs written by this company, right? I mean, they go on forever, right? There is no notion of termination if you're talking of operating systems or anything like that. So I think, relying on termination and asking questions after the fact is it's nonsensical in this domain. It has to be continuous. What's going on? Is it legal or not legal? And I'm saying the current Java memory model definition does not satisfy that. And I'm not saying I know the answer. I mean, if you're going to allow such optimizations, you have made the problem impossible. I mean, something has to give in this.
Right. Now, what's this optimization?
Let me see if I can reproduce it very quickly. So, I think what happens in this is...
Actually, Arvind, can I make a suggestion?
Yeah.
Why don't you wrap up the talk?
Yeah, I'm done, I think. Yeah, right. Yes, sorry. So, I think this was the last slide. That, there is a lot more to be done from architectural point of view also, because what I have shown you here is there was no cost metric in my work. In this work, all we were trying to figure out is what is legal and what is not legal. But as an implementer, you want to do these things very, very efficiently. And the biggest sledgehammer you have is to take many of these decisions so early, because there it doesn't matter if you rule out behaviors. You just have to pick some of the legal behaviors that are permitted. Yeah.
If I understand you correctly, these extra magic edges that you draw
Right.
do not have an algorithm?
I have an algorithm for drawing them, but it's very inefficient. I mean, it's really meant for theoreticians. It's nothing that architects would ever want to do, right? Because it's much simpler. The moment you do two stores, just draw an edge between them and get it over with. And it's correct. It's going to preserve store atomicity. Right. I'm sorry the talk is a bit open and it doesn't have a proper summary.
Let's thank the speaker.
Yeah, thank you.